so I can achieve all positions L sine theta if I have the ability to manipulate L and epsilon, right? Okay. So you can keep doing this, and this will rotate the entire body to the angle that you want, in addition to desired angles psi and length L. So you can reach any final configuration L, some psi and some theta. Okay. So now we're going to add one level of complexity to that. We're going to include dynamics. So actually I have a force here. Now my control inputs are not just L dot. This is too much to ask. Maybe the time scale of the actuator here is not that fast to say I have a direct control over L dot. No, you have direct control actually on the force. So I have a force here. Let's put it somewhere, maybe let's put green. So I have a force here. This is F. And I have a torque, tau. Okay? And let's see what do we get. What do we get from the controllability of that system, with the understanding that at least I should be able to get configuration kind of thing, right? Because we had this from before. So let's see what do we get. Your kinetic energy, right? So I will not derive it. It's it's super easy. You can actually get it from first hand here. It's 1/2 I theta dot squared for the body, and the arm is 1/2. The arm is massless, so just I have the mass up there. I have L dot squared plus L squared, right? Just L, I guess. Yeah, psi dot theta dot squared. Yeah. I omega squared. So this is, I guess this is L squared as well. Yeah. Okay, so this is my kinetic energy. So let's do the equations of motion. There is no potential, so V is 0, d by dt, partial Lagrangian, partial L dot, minus partial Lagrangian, partial L is your force, right? So this guy, you get ml double dot minus, when you differentiate this with respect to L, you get ml psi dot plus theta dot squared equal the force, your first equation of motion. You can do the second for psi, so d by dt, partial L partial psi dot, you get what? D by dt, and do it carefully please, because this is ml squared psi dot plus theta dot. All of them are time varying except the mass. So you get ml squared psi double dot plus theta double dot, and L is time varying too. So this is 2 ml L dot psi dot plus theta dot, right? And this is the torque that you apply on the arm. For theta is very similar, it's actually d by dt. You get I theta dot plus the same term here. So you have I theta double dot plus these guys again equals 0. And you can lump them in our usual form, mass times acceleration plus some centripetal and Coriolis forces equals something in the force plus something in the torque. And we can fill that very easily. It's like mass ml squared, ml squared, ml squared, I plus ml squared, right? 0 otherwise. Here is negative ml. Yeah, negative ml psi dot plus theta dot all squared. As you can see, these are quadratic in velocities. 2ml L dot and the psi dot theta dot again quadratic in velocities. Actually get the same term, exactly the same. 1 0 0 0 1 0. So actually this is my first control input U1, my second control input U2, control force, vector field and vector field. So this is what? This is my C of QQ dot, right? The centripetal Coriolis, This is my mass matrix, and this is Q double dot. Any questions so far? Just direct application of mechanics. I'm gonna invert. So L double dot, psi double dot, theta double dot. This is, the first is easy, just divide by m, so this is negative L. The second is a little bit, you can just do it on your pace. I remember we divide by ml here, so this is L dot, this guy divided by L. Here you get 0 actually. And here, again, this is 1 over m, 0, 0. This is u1 plus, here is 0. And here is 1 over I plus 1 over ml squared. I think this is negative 1 over I2. So what's that? This is the geometric acceleration, very good. And this is my first control acceleration vector field, my second control acceleration vector field. So the family y is just y1 and y2, okay? Okay, so let's study the controllability of the system, mechanical system like we did today. We'll do it using just the force only, the torque only, and both, okay? And to do that, we're gonna do symmetric products. Symmetric products means we need covariant derivatives if you wanna do it this way. So covariant derivatives we need what? To do a derivative, what do you need? Christoffel symbols, very good. So let's get the Christoffel symbols, which is super easy here. This is the way I like to get. Don't go and, you can play with the Riemannian metric and do the definition and everything. But actually from here, this is super easy. So look at this term and extract your quadratic form. So this gives you gamma L. I'm sorry, I already wrote it right. So gamma L is what? So what's multiplying psi dot squared is negative L. I have here L psi dot theta dot L psi dot theta dot. What's multiplying psi dot squared? So the element 2, 2 is negative L. Theta dot squared is also negative L. Psi dot theta dot is 2 negative L, but I'm gonna divide them by negative L and negative L, right? So that's it. This is 0, zeros. The same for this guy. Gamma psi, this is the psi equation. Again, it's L dot psi dot, it's 1 over L here and 1 over L there. L dot theta dot, again 1 over L here and 1 over L there, 0, otherwise we're done, right? Super easy to get the Christoffel symbols, which, you know, it's like a nightmare for physicists. But because we have the equations of motion, so we're cheating. Theta equation is 0. So no quadratic forms. Okay.
But in the psi Christoffel symbols you have an L dot.
Yeah, L dot that multiplied psi dot, right?
Oh, you did?
Yes, it's just, there's no L dot squared over it. Okay, psi dot squared, L dot squared. We got the Christoffel symbols. You can apply the very routine definition if you like. And let's do the symmetric product. So I need the symmetric product. So first problem, let's do using the force only. So just extend back and forth. Let's see what do we get. So using the force only, so we have just u1 only. So my family is just y1, and y1 was 1 over m is 0, 0. Just one vector field. Okay, I'm going to do symmetric products. So unlike Lie brackets, we don't do Lie bracket with the vector with itself, it's 0. Symmetric product, there is a thing. And this is just apply the definition, apply y1, y1 plus apply y1, y1. So this is 2 of the same, right? And we can go and do it using MATLAB. So I have a very little script here. So I do sims mass, inertia, L, psi, theta. These are your coordinates. My configuration coordinates are L, psi, and theta. My y1 is this guy. My y2 is that guy that we got. I give it the Riemannian metric, the mass matrix, right? These are the components of the mass matrix, ml squared, L squared, and we have here I plus ml squared. And then I wrote this guy to get the Christoffel symbols out of the Riemannian metric. The very boring definition, but the computer will do it. Okay, so we got gammas. Then what is y1, y1? Like I said, this is twice the covariant derivative. So again, I did a very little script that takes q's, Christoffel symbols, the two vectors, and give you the covariant derivative. And I need two of that, so let's run this guy. So the y1, y1 is zeros. So actually, when you do symmetric product here, it turns out that this is zero. So no further, yes please.
I have a question. How did we get y1 to be equal 1 over m and g?
Not G.
It's zero.
Super sloppy. It's two zeros.
Oh.
Sorry about that. Thank you. Yeah. Okay, so this is zero. So it's not zero after substitution. It's zero, for everywhere. So you cannot do more symmetric products. So actually, the infinite iterations of symmetric products of the family Y is just the span of Y1, which covers just one dimension in the tangent bundle. Here we don't have non-holonomic constraints, so I should cover the three-dimensional space, so this is definitely not R3. So what you get, the system is not what from here? Not accessible, very good. Not accessible, and if it's not accessible, of course, it's not small-time locally controlled. But there is a hope to be configuration kind of thing. Well, so I need to do the Lie infinity of sim infinity.